Alright, welcome to day 1 of chapter 19. We're going to be talking about reactions of aromatic compounds. So the title is Electrophilic Aromatic Substitution, and we should be able to draw lots of information just from the title already. We can first review what electrophiles are. Remember, they love and they want to take electrons. They generally feel positive and they want to get that charge not so strong by evening it out with some negative electrons. So electrophiles. Aromatic, we also remember they tend to be planar unsaturated rings, and our example today is definitely going to be benzene. Substitution. So when you use a substitute, you're putting something in place of another. So on our benzene, we're going to take hydrogen or another group off the ring and replace it with something. In our case today, we're only going to take off a hydrogen and replace it as a substitution. But I guess the main question is, where can an electrophile who loves electrons find them in benzene? So if you look at benzene, these aromatic compounds have that pi system where they have all those delocalized electrons in that ring. And so that's where our electrophiles are going to find electron density in our benzene, from the pi system. So here's our general reaction already, very general, just to give you a first look at it. So step 1, we get an electrophilic attack of the pi system of benzene. So here we go. We get electrons out of the benzene being dumped into our electrophile, and we get this intermediate, because we do have a step 2. So what's the problems with this intermediate? Why don't we just stop here? Well, 1, it has a positive charge, which it's not real happy about. And 2, you just broke the aromaticity. Okay, so even though this is an intermediate and it does form and it's going to be stabilized, we'll see why in a minute, it's not quite as happy as it could be. So step 2, we deprotonate. Okay, where did the base come from? Well, usually it was attached to the electrophile in some way. We're going to see how those are formed in a minute, but that Lewis base will then pull off that hydrogen, put those 2 electrons from the hydrogen bond into that carbocation positive charge, and give us our substituted benzene, which has restored aromaticity, and some other products. Okay, so there's our basic reaction. Well, wait a minute. Some of you out there might be thinking, this is throwing a wrench into my thinking. Didn't you say benzene was inert in a previous chapter? Because when we talked about addition, okay, we had cyclohexene, we threw some bromine on it, and we got the 1,2 addition. And then I said, if you take benzene and bromine, you don't get that reaction. Okay, well, this is true. But we're going to look at these reactions of aromatic compounds because we can do them. You're going to see that if we have bromine and some other small catalyst, you can get the substituted product. So benzene is mostly unreactive, which was actually different than completely unreactive. So we do get processes like this substitution. Okay, so key. Here's a key slide. Make sure you're taking notes. This is our key generic mechanism. So we have some kind of an electrophile having electron density put into the electrophile. This part is slow. We form a carbocation, but this is a sigma complex that is stabilized through resonance. If we remember our arrow pushing, we can push, and we can form these 3 resonance structures. And the more resonance forms that we have to distribute that positive charge and make it feel less egregious, the better off and more stabilized we can get. So we have this stabilized complex. Step 2, if you remember, we had to take the hydrogen off. So what happened up here, once we had this electron density go into the electrophile, it pushed these electrons up onto this other part, this Lewis base part, which made it really negative, enough so that it will pull off this hydrogen fast, throw these 2 electrons back into the ring, and give us our substituted product. Okay, so questions about that? All right. But it is a key concept to know why we get an addition product from cyclohexene and not benzene. Okay, so if we look at this first one here, where we have no bromine addition across benzene, but we do have the substitution. The addition reaction here, if we look at this, it would break the aromaticity, and that is very destabilizing. We do not want that. So it definitely does not want to go the addition reaction with bromine and iron bromide. But if we look at our addition product, why does this not want to substitute bromine on here? Okay, well, the key is this does not have the same electron density in the ring that we need for this substitution. Okay, it does not have that enough electron density for that electrophile. But the beauty of this reaction is that these electrophiles can be lots of different things. So here's a good chart in your notes if you print off this slide and the next one to study. So we're going to take benzene and we're going to look at all these different reactions. And if you look, they're numbered at 1, 2, 3, 4, 5, so on and so forth. And what you could do as you study this, if you print it off back to back, you can look at your halogenations and try and think of the different reagents and memorize the reagents you can use and test yourself. Because on the other slide, see all these reaction numbers, give the name, give the general conditions that you would use for it, and any side notes or things that you should be aware of. So this start quizzing yourself or in a study group. This one really, these two slides really help. So we're going to start with a halogenous benzene, which is right here. And it happens when you generally treat with a diatomic halogen. And we're going to talk about chlorine and benzene as the Lewis acid catalyst. The halogen and Lewis acid react first together to form a better electrophile. That's what's important. And in this case, the active electrophile is bromine, chlorine, and iodine plus 1. Now I know some of you are out there saying, say what? Aren't these all supposed to be negative 1s? That's what Gen Chem taught me. But you also have to remember, we did have some special cases in Gen Chem. We said sometimes they can be positive. So it's important to have that Lewis acid catalyst to make these electrophiles. So how do we make these really reactive electrophiles? This is how we do it. We're going to take our bromine, add our iron bromide catalysts, and we form this crazy intermediate, which is a much stronger electrophile than bromine itself. So we have molecular halogen, we have our Lewis acid catalyst forming our really strong electrophile. And here's our reaction. We're going to walk through it here. So we have this electron density going into our bromine, pushing our electron density onto that cation. Okay, so that's where we're helping our electrophile become less positive. And we're going to form our stabilized sigma complex, just like we've seen. And then this Lewis base here has enough negative charge to pull off that hydrogen, push these electrons in here, and give us our substituted product. So the question is, why is iron bromide considered a catalyst? Okay, well, because this is actually what started a whole reaction is our Lewis acid catalyst here. And so once this is formed in a product, it can go back into the mix, do it again and again and again. Okay, so other combinations of halogens, the chlorination will come from chloride and aluminum chloride. Iodine's a little bit different. We're not going to really talk about that one here, but you can do it with iodine and nitric acid. If we look at our potential energy diagram here, it's important to know certain things here. So our first step is highly endothermic. It's very energy intensive. It is our rate limiting transition state in our first step. Okay, so we go way up here in energy to go through that first transition into our sigma complex. Now, we do get a lowering of energy, but it's still relatively high. So it's stabilized through resonance, but it still doesn't want to sit here. Okay, now it's very reactive and it's no longer aromatic. We've got to fix that. So our second transition state, which was fast, gives us a highly exothermic product. How do we know it's exothermic? Because the product energy is lower than the reactant energy. Okay, we could get, if we look at the energetics, we can actually calculate this. If we look at the energetics for the addition product, there is a possibility of getting it, okay, but it's very high in energy. It would not be stable. It would not sit here. It's not very probable when it would rather form this. Okay, so the question is, how do we know that the intermediate is so highly reactive? Well, one, we see the energy is high, but two, we know we broke aromaticity is a problem. And why is the substitution project so much more stable? Again, has to do with the aromaticity. The addition product would no longer be aromatic. All right, so moving on to, so we did halogens. Let's look at the nitrations. Still getting that electrophile. So our reagents here for this to form our NO2 plus electrophile is an interaction between sulfuric acid and nitric acid. And what happens is the nitric acid pulls the proton off the sulfuric acid, and then we get this complex formation, which then pushes these electrons onto here to form water. So we do form water, but we form this nitronium electrophile ion. See, it's a nitrogen with a nice positive charge sitting on it. So why is basics? Let's look at Gen Chem. Why was the sulfuric acid the proton donor and the nitric acid the proton acceptor? Well, if you look at them relatively, one is stronger acid than the other, and they follow basic acid-base rules. So here's our electrophilic aromatic substitution reaction. Again, this should seem fairly normal. We're putting electron density into the nitrogen in this case, okay, because we have that room there, and then we could push the electron density up to the nitrogen, which gives us this sigma complex, which again is stabilized through resonance. Now, we're not showing that nitrogen negative up here, but there are things with this group that we're going to talk about quite a bit later at the end of today. Also, I wanted to note sometimes when you see online, instead of the 3 resonance complex written out like this, sometimes they just show that that positive charge can be distributed around this ring, and this is how they draw that hybrid. Okay, so our second step, our fast step, is that loss of protons. So actually water in this case is what's acting as our Lewis base. We're pulling this hydrogen off of here, throwing those 2 electrons back into this ring to give us nitrobenzene and hydronium. Okay, note, we like making these. We like putting nitrates on benzene because from what we learned before, they can easily be reduced to amine. So if you don't want a nitro group, but you do want an amine, it's easy to throw the nitro group on and then reduce it to amine, because all you got to do is throw in some zinc, tin, iron, a little bit of aqueous media, and you can reduce that to a substituted amine instead. Okay, our next reaction is the sulfonation of benzene. So we're going to put a sulfate group in there. Overall, you just throw in some sulfuric acid, no nitric. Throw in a little bit of heat, and we get the sulfonyl SO3H group and water. Our general mechanism. So you should be able to, we've seen enough already that we should have some idea. So this electron density is going to be pushed into our electrophile, but this in and of itself is not our electrophile. How do we get that strong electrophile? Okay, well, sulfuric acid can autoionize like this to give us the SO4H3 plus, and then we can get some electron rearranging to give us this SO3H plus our HSO4 minus. So this is important, and the water is important. So this is good to know generally what's happening here, but I'm never going to have you write out the arrow, the electron arrow pushing for this here. But again, you should know that this negative compound is there, the SO3H plus is there, and water. All right, so the last line is our actual mechanism. We have benzene. Ooh, now be careful. Students a lot of times will automatically take the electrons and push them into the positive site. Nope, that's not the case. Oxygen is electronegative and it likes electron density, but where this is going to put electron density is into the sulfur. Remember, sulfur is a weird atom. It takes and likes a lot of electron density in all those orbitals. So we're going to put the electron density in the sulfur, and then we're going to push these electrons up onto the oxygen. Okay, so that way we get our complex here, which is still stabilized through resonance. All right, here's this HSO4 minus. That is going to pull off our hydrogen, push the 2 electrons down in to form our sulfonation of benzene. And again, we reform our sulfuric acid, which can go right back into the mix as a catalyst. Okay, questions? Look at that real for just a minute. All right. You must know the arrow pushing for this last step. One other thing about the sulfonation of benzene. So one reagent that wasn't in the mix that you saw is SO3. And if you can throw SO3 in there in the mix, it's a really strong electrophile of its own right, because overall it is neutral, but it has lots of resonance stabilizing structures. So here's our SO3, and if we do some of our resonance forms, we can see we have lots of different resonance form, and it does make it a very powerful electrophile. And if we look where the charge is located in our electrostatic potential map here, we have mostly our positive charge here and our negative charge out here. Okay, that's why we like to put electron density into the sulfur. But a key thing, if you're taking, well, you should be taking notes, and that's what these little puzzle pieces are here for. Put a star by this. Our electrophilic aromatic substitution is the only reversible reaction we're going to look at for EAS. So what happens once you take your sulfonation product here? If you take water and sulfuric acid, you can pull that back off to reform your benzene. Now, if you're with me, you should be thinking, your little brows should be going together thinking, now wait a minute. Don't we make sulfuric acid, and won't that automatically desulfonate and just give us benzene? Why do we bother running this reaction? Because we're never going to get the sulfonated product. We're always going to push it right back towards the benzene. Why would we do this? Well, in chemistry, there are things that we can do. So we can use a little bit lower temperatures. So even though this did require heat, as long as we don't go too high, that will help push it towards this product. And we can also chuck in, the reason we were talking about SO3 is we can throw in some SO3 to help push it to the sulfonated product. Okay, so if we use high concentrations, that will make a difference. Also, if we have lots of excess H2SO4, we can also push this and keep us from doing the reverse reaction and just getting benzene back. Okay, so let's do a quick review of our chart. What have we done so far? We've done our halogenation, we've done our nitration, we've done our sulfonation. The last two we're really going to look at is then our Friedel-Crafts. We have Friedel-Crafts alkylation and Friedel-Crafts acylation. Okay, one more review. We're going to look at these, what was our cation or our electrophile needed, and the reagents, just to get it through your memory one more time. Again, puzzle piece here means there's some things on your student notes to fill out, so make sure you're doing that. All right, so the bromination with an iron catalyst. What was the product? Well, we just substituted a bromine on there. What was our cation or electrophile? Was bromine plus. How did we form it? Well, we had bromine interacting with our Br3 to give Br plus and FeBr3 minus. Memorize. Okay, we can do a chlorination. We didn't look at that mechanism, but it is basically the same. We're going to get a chlorine substituted on there. The electrophile that we need is the Cl plus, and it's basically the same type of interaction, just with aluminum chloride instead of iron bromide. Nitric acid and sulfuric acid, that was the nitration. Okay, so we got an NO2 group here. What was our electrophile? NO2 plus. And we formed that by interacting nitric acid with sulfuric acid to give these three products. All right, have we seen this one yet? No. An alkyl halide. Nope. Ooh, nope, haven't seen that one yet. Must be coming. All right, SO3 and sulfuric acid. This was our sulfonation. What happened? We got the SO3H substituted on there. The electrophile we needed was SO3H plus. And how did we form that? Well, we had SO3 or H2SO4. That's why I said I'm not going to ask you for the arrow pushing per se. But you should know that these things interact to give SO3 plus and HSO4 minus. Okay, so the last two we're going to look at is our Friedel-Crafts alkylation. So this is an alkyl group. We're going to substitute that alkyl group on there with an R plus as our electrophile. You're going to see that you get a similar reaction or similar interaction to as up here. And we're also going to do this, which gives us this oxygen double bond alkyl group here. This is a little bit different. This is our electrophile that we used. And we're going to see an interaction to give us this acylium cation. Okay? All right, so comparing the two real quick. So the first one is the alkylation. We're going to put the alkyl group on there. But there are some criteria that we're going to talk about. First, it must be an alkyl halide. Chlorides, bromides, iodides, it's fine. The Lewis acid often used is aluminum chloride. You can also see, if you look it up, you can see some iron chlorides and zirconium chlorides, but it's almost always a chloride here. And one thing you want to put a star by here is our carbocation rearrangement. So that's going to be an issue that we're going to talk about in a minute. Also, one drawback is you cannot use it with alkenyl halides or alkenyl halides. It just doesn't work. Okay, so there are some problems here. The acylation uses this acyl group. It looks like this. Usually X is some kind of halogen. Chlorine, bromine, iodine. You can use anhydrides. We're not going to look at these, but you can do this with some anhydrides also. All right, so let's go through the alkylation. Secondary and tertiary alkyl halides. So adding aluminum chloride leads to the formation of carbocations. Okay, it does. They are excellent electrophiles. So if we look at the secondary alkyl halide, the chlorine will put electron density in the aluminum. Remember, it's a big transition metal. It's got lots of room sitting in these orbitals. We're going to put it into the aluminum. We're going to have this interaction, which then the electron density pushes back onto the chlorine, because this does not like to be positive if it can help it, and we form this secondary carbocation. All right, so this should start to look familiar. We're going to take this electron density, we're going to put it into this carbon with a positive charge. We get, okay, this, I've seen students draw really weird things. We are getting a bond between this carbon and this carbon. That's why you get this form here. We still have a resonance stabilized carbocation here. We had our nucleophile still interacting with our electrophile, and we have our resonance stabilized sigma complex. So lots of terminology that you're learning through this. This is also, if you haven't caught it by now, this is our rate limiting slow step. Our second step is we take the electrons here, pull off this hydrogen here because this is our Lewis base. These two electrons get pushed back into the ring to re-aromatize this with our alkyl substituent. Okay, we regenerate our aluminum chloride, which then goes right back in as our catalyst to go through the reaction again. Okay, questions? Think about this. If nothing else, pause your video and look this through and make sure this all makes sense. Okay. Driving force in all these reactions is you're restoring aromaticity and lowering that energy. Okay, so limitations. One. That means there's more than one. Well, primary alkyl halides undergo rearrangements and would rather form secondary or tertiary carbocations. We found this before. We talked about this before. We don't like to have primary carbocations. So if you have this primary alkyl halide interacting with your aluminum chloride, yeah, you're going to get a positive charge here, but you get this 1,2 hydride shift, this rearrangement to give you the secondary carbocation. So we get the reaction that we just had on the last slide, okay, because that is stabilizing through inductive effects. Okay, that primary carbocation is very unstable. Okay, remember, those were inductive effects. So if you take this primary alkyl halide with aluminum chloride, yes, you can get some primary product, teeny minor, but through our 1,2 hydride shift and our rearrangement, we get this as our major product. Okay, so that's a drawback. Drawback 2 and drawback number 3. Drawback 2, aryl halides and vinyl halides are a no-go. Okay, so aryl halide like this, vinyl halide like this, we've got these sp2 hybridized carbons, you're going to get no reaction. Okay, so you can't do it with those. Number 3 is it's hard to stop these reactions at only one or a monoalkylation. Okay, so if we take something like this, methylene chloride here, and do our substitution, yes, we get 1, but then we get 2, 3, 4. We can get more substitutions than we want. If we only want 1, this becomes a problem. Okay, so what instrument, I know we've talked a little bit about this, what instrument could we use to see if we got the mono substituted or if we accidentally got lots of substitutions? Think about it. What instrument in the lab could you use? Okay, good instrument is an NMR. You're going to see a different splitting pattern depending on how many methyl groups you had substituted on there. Uh-oh, are we starting to see drawbacks of this reaction yet? We're on number 4 of our limitations. Some substituents can be deactivating. Okay, these are some substituents. I'll tell you what this means in a minute. So nitrate groups, cyano groups, sulfates, okay, ethers, things like this. So if we're trying to put an alkylation on there and it already has a nitrate group substituent, this is what we call electron withdrawing. So what this does is this likes electrons so much it pulls electron density out of this ring. And that's due to the resonance in the NO2 substituent here. It likes to pull these electron density and delocalize it. Okay, so think, why would that cause problems to an EAS reaction? Think about it. Well, if it's pulling electron density out of this ring, that means there's less electrons to be dumped onto our electrophile. Okay, and you're going to get no reaction. It's deactivating. Even though we know this will run the reaction, having this group on there is going to deactivate it. All right, why? Because you have less electron density to be able to give to your electrophile. Okay, last but not least, number 5. If you already have an amine substituent on your ring, so instead of a nitrate here, you have an amine sitting on your ring. Aluminum likes amine so much that instead of running your substitution, that aluminum sits on that amine, and it sits there very happy because it pulls lots of electron density up into this nitrogen and into that aluminum. It completely kills your Friedel-Crafts reaction. Okay, so amine substituents on there. These substituents, which are electron withdrawing, are deactivating, can be problems. All right, pulls electron density out of the pi system. That's the main key. All right, so we just wilt like this plant, and do we give up? No, of course not. Some really cool person came up with a solution, and it's very similar to the acylation. And you need to realize acyl is just an old-timey name for a carbonyl. Okay, so for example, we have benzene with ethanoyl chloride and aluminum chloride with a little bit of heat, and we form this acylium ion. So in the one slide you saw it drawn just with your bond structures. Here I have the carbons written in there. What you get is you do get a product complex, a little bit of water, and you do get your substitution of this acyl group. Okay. Aha! The product is less reactive than the ketone. Sorry, product is less reactive than the reactant because the ketone is activating. So if it's, deactivating. Goodness. If it's deactivating, is it pushing electrons in or taking electrons out? Okay, it must be withdrawing. All right, so let's look at it really a lot closer. But the key to this is, why did they come up with the acylation too? The rearrangement is not possible with this. Okay, so if we have an acyl group, we're going to put electrons into, remember aluminum is transition metal, lots of room in those orbitals. We're going to put electron density into the aluminum. We're going to make this complex. We're going to put electrons into that chlorine because it doesn't want to be positive, and we're going to form this acylium. But what's missing, because I see students do this all the time, what did we forget to put here? Okay, carbon doesn't like to have only 3 bonds. It has the positive charge. There's our acylium. But it looks like it would be really, really unstable. But if something looks unstable, maybe it has resonance stabilization, which it does. So if we have 2 electrons here pushed down in to give us 3 bonds here and 1, so 4 bonds on carbon, and push that positive charge onto oxygen, which we know it doesn't like, but it's still a resonance form, and it's stabilizing. Okay, and we still get our AlCO4 minus as our Lewis base. All right, so first step. Here's our big puzzle piece. Make sure you're taking notes on this. Pi system goes into, the electron density goes into the carbon. Okay, so direct right at the positive site. We do get this here because we're forming a bond between this carbon and this one, so we get this bond between this carbon and this one here. We form our carbocation, which again is resonance stabilized. I've seen this 10 times already today. And then what happens? So we can't have this hydrogen here. We have to restore aromaticity. So our Lewis base, our AlCO4, which is negative, will pull off this hydrogen, push that electron density back into the ring to give us our aluminum, a little bit of hydrochloric acid, and our substituted product. Okay, so also vinyls and tertiary alcohols. You can see in your book there's an example in these two figures. Questions? All right, so electrophilic aromatic substitution. So here's our chart. We've covered all of these. The only thing that we didn't cover that you should look at this point, so we didn't look at reactions 11, 12, and 13, where we take our acylation that we just looked at, and you can actually reduce those down to your alkyl groups. Okay, so that's a nice synthetic step that we can do, and there's a few of those. Also, we didn't look at if you have an alkyl group already on your benzene, you can do some side chain oxidation to get things like your carboxylic acids. Okay, so you'll leave that up to you. Oh, also you could take your alkyl groups and brominate them, so on and so forth. We saw lots of these reactions in your alkyl halide sheet. Okay, so last thing we're going to cover today is diasubstitution, polysubstitution. So what happens if you already have a substituent on your benzene? So in this case, in this table, we have an alcohol already, a methyl group, a chlorine, a nitro group. What happens if we now want to nitrate those? So we want to throw an NO2 group on all 5 of those compounds. What do we use to nitrate rings in EAS? Okay, nitric acid and sulfuric acid. And if we look at these, which one do we think would be substituted slower, and why? Okay, well, in a previous slide we did talk about the NO2 group was deactivating. Okay, so when it's deactivating, is it of these the most electron withdrawing? Yes. NO2 we said was very electron withdrawing. And why? Why is because we had resonance across that NO2 group. And we're going to look at that here in a minute actually. Okay. And if that's the most electron withdrawing, is it going to increase the rate or decrease? And why? All right, we discussed this a little bit already. It's going to decrease the rate because it's pulling electron density out of its electron withdrawing. It's pulling it out of that pi system. And that's our driving force for EAS, taking that electron density, throwing it onto our electrophile, so on and so forth. Okay, so if we look at our rates, the alcohol group is the fastest. Okay, so if electron withdrawing slows it down, deactivates it, alcohol groups must activate it. But why? So if nitrate groups are electron withdrawing, OH groups must be electron donating. They must be pushing electron density into that pi system, which means there is even more electron density to go to our electrophile. Ah, okay, faster. Slowest. If we want to nitrate this, this is pretty darn slow. And then these go in order. So methyl group is a little slower, still faster than a hydrogen because of inductive effects. Here's just a regular old benzene. And then chlorine is slower, so it must be, is it electron withdrawing or electron donating? Ah, it's electron withdrawing, slower. All right, so we now know that it can cause issues depending on if it's electron donating or electron withdrawing. But we need to address now, does it make a difference what position the substitution happens? If I have a substituent, I don't like that your book puts an X on here. This should be any kind of group. You think it's an halogen, but it can be anything. Doesn't matter if we're going to substitute at the ortho, meta, para positions. Yes, it does. If in this case, if we had a methyl group sitting here, experiments show that it directs the substitution mainly to the ortho and the para positions. Oh, so substituents can affect our rate. They can either speed it up or slow it down, and they can also direct the substitution to certain positions. This is not sterics. This is fully electronics. It has nothing to do with how bulky at this point this substituent is. That's not what's going to push it here or there. Okay? These are called orthopara directors. So not every, as you can see now, not every EAS reaction occurs with just benzene. So if we had toluene here, if we had a methyl group on and we wanted to nitrate it, all right, so we've got our nitric acid on our sulfuric acid. We can get the NO2 group here at the ortho. We can get the NO2 group here at the meta. And we could get it here at the para. Now, some people are out there thinking, oh my gosh, I have to memorize those percentages. No, you do not. But you do need to know that you are going to have more ortho and para than meta. This is an ortho-para director. Okay. Suddenly there are both changes in rate and regiochemistry. So this was a little fast on the faster side just because of inductive effects, but it is going to direct ortho-para. All right, so let's look at this really quick. First, I want to make sure that we realize that this is an activated group because of inductive effects. And when we push electron density into this ring, that means we have much more electron density to put on into our electrophile. Okay, much more availability. So here we push it onto the nitronium, push that electron density up here. We got our NO2 group on the ring. Okay, resonance stabilized. But look, there's a reason why this ortho position is really self-selected over, it's directed to this ortho position rather than the meta. Why? Because we do have a resonance form that puts the carbocation right here at this tertiary carbon, and this methyl group has inductive effects, so it pushes a little more electron density into this positive charge well here, and it helps to stabilize that. Okay, it makes this feel less icky, less positive, and we know chemistry likes not to be charged if possible. Okay, so that's why that's an important. Let's go look at the para. Same thing, we can push it here, and if we look at this in the para position, if we look at all the different resonance forms, we do get one again that has the carbocation here at this tertiary carbon with inductive effects. But did we get that with the meta? Well, if we look, substitution, we have a positive charge here, we have a positive charge here, we have a positive charge here. No, we do not get that carbocation at that tertiary carbon right here at our methyl group. We're not getting help from that inductive effect to stabilize one of these resonance forms. Okay, so great question. If certain substituents direct to certain spots, can they also affect the rates? Yes, remember, they can either be activating or deactivating, and they can also be directors. Okay. So activating and deactivating group. Let's look at these in general, now that we know the idea. Okay, examples of orthopara directors. We have all these examples here. So these are going to be orthopara directors, and they're going to do so off of that resonance form stabilization. Now the thing is, if we look at these, they're orthopara directors, but they are deactivating. Okay, they're going to direct, but they're deactivating. So activating groups tend to donate electrons. We've talked about this. This will be like the third or fourth time you heard it, so hopefully it's went in. Deactivating groups tend to withdraw. Okay, so these are all strongly activating it. These are deactivating. Okay, so do we have certain, we're going to look at this, cyano group, nitro groups, strongly deactivating. And why? Because they're pulling electron density out of that ring. And these are in the middle just because they tend to be, they're deactivating, but they're not necessarily withdrawing. They are and they aren't. Those are our main ones. Okay, note, these are not on our orthopara director list. Okay, so let's go through some examples here real quick. So what are these reagents doing? They're putting a nitro group on our ring. Okay, OR, so this is our ether, this is activating. So it must be electron donating, which means it will speed up our rate. Okay, if you look at your list, ethers are orthopara directors. So we're going to get ortho, we're going to get para. Will we get some meta? Yes, a little bit, but not much. This is an orthopara director. Okay, how about an alcohol group? Okay, we're just putting the nitrate on there. OR is activating, electron donating. And again, if you look at your table or your list, because I know you haven't memorized it yet, it's orthopara directing. Okay, this really should say sulfuric acid down here too. I should change that. Major, ortho, para, and minor, meta. All right, same thing here. What if there's a cyano group on there? All right, well, cyano groups were electron withdrawing, so they must be deactivating. Slows our rate down. It was not on our orthometa or orthopara director list, so this must be meta. Okay. Well, hello, meta directors. Electron withdrawing dudes, especially strong ones like cyano here, are electron withdrawing groups. And if we look at our meta directors, which were on that table that we highlighted, you're going to get a major product is the meta position, a minor orthopara. All right, so major is meta, minor is orthopara. All right, here's a nice chart. This is going to help you. Activating and deactivating, so they're either going to speed up the rate or lower the rate. And directors, orthopara, and meta directors. You do not have activating groups that activate meta directors. Okay, so activating groups increase the rate. Deactivating groups decrease the rate. Remember that the alkyl groups are electron donating through inductive effects, so we have this tertiary, secondary, primary carbocation stabilization. And when we're pushing electron density into that aromatic ring, the pi system is more electron rich and therefore can interact with our nucleophile faster reaction. Okay, this is a great chart to help you study. Last but not least, let's look at this here about activating and electron withdrawing and electron withholding. If we just compare benzene to our methyl substituted, our amine substituted, our nitrate substituted, if we look at our electrostatic potential maps, regular benzene has, okay, here's our red is positive, is our negative charge. So here in benzene we have lots of negative charge associated with our ring. Here we have our methyl group. It's inductive, but only slightly enough in that it's pushing a little more. You can barely see that it's got more red in there, but it does. It's not got red up here. But as soon as we put an amine on there, look, this red, this negative charge starts to bleed up into the nitrogen. Less electron density in the ring. And if we go all the way to the nitrate group, which we've been talking about a lot, this should solidify it. Look at, there's so much less negative charge sitting in this ring because it's been pulled up into this NO2 group, and here is our resonance. So if we look at it, we have resonance forms of N plus and O minus, and if we look at the resonance, you can put a minus here and a plus here. You've got resonance up here that pulls that electron density up into the nitrate. Okay, so that is our difference with our electron withdrawing. And if we have so little electron density sitting in here, we can't use it to drive our EAS reactions. Okay, so wrapping it up, we would have a handful of minutes here. We can propose a mechanism. Oh, I've got the misspelled word up there. And we would go through and I would have you guys follow through. You should, if you're watching this video, actually, you should pause it right now and see if you could go through the arrow pushing of this example. If we run out of time in class, we'll basically do this when we start the next class. I would like you to be able to write these. If you didn't get this fourth resonance in your paper because you had all these blank spaces, you may not have realized that there is a fourth one with this ether. You do need to realize that this is your Lewis base, pulls off a hydrogen, and gives us this product. Okay, wrapping it up, we have another question about aniline here. Talks about the reagents used for sulfuric acid. Okay, so we would get a protonated form of our aniline. Talking also about if it's an activating orthopara director, so on and so forth. Also The acyl group removes, how it removes some of the density, and how this would affect the reaction. And then we could go over some of our takeaways. What does it take to benzene to react? Do you know what electrophiles and where the electricity density comes from? Can you generally describe the mechanism? Can you remember some of the reagents? What does induction mean and how is it different from resonance? What similarities do all activating groups have and deactivating groups? What similarities do orthopair directors have and metadirectors? How can substituent effects on electrophilic aromatic be explained in terms of mechanism or reaction diagrams? Next time, we're going to look at a little bit more about directors, activators, deactivators with a group work problem set, and then we're going to finish up Chapter 19 with nucleophilic aromatic substitution. Day 2.